We've all seen a glass shatter or an egg break on the floor, but you have never seen a shattered egg pull itself together, lift off the tile, and land perfectly intact back in your hand. Time, as we experience it, is a strict one-way street. But if you dismantle the universe down to its mathematical bedrock, you run into a rather disturbing secret. The equations of motion developed by Isaac Newton do not care which way the clock is ticking. If you replace every positive value of time with a negative value, the math works exactly the same. Physicists call this time reversal invariance. If you record a video of two subatomic particles colliding and play it backward to a room full of experts, not a single one could tell you which direction is the future and which is the past. Down at the microscopic level, reality is completely symmetric. Yet zoom back out to our scale, and that symmetry vanishes. When you drop ink into a glass of water, those individual microscopic collisions are perfectly reversible, but collectively, they create a chaotic swirl that will never spontaneously unmix. We are left with a system built entirely out of reversible parts, but which behaves in a completely irreversible way. Some hidden rule is forcing the universe onto a one-way path. In the late 19th century, Austrian physicist Ludwig Boltzmann suggested that to understand time, we have to stop looking at individual atoms and start looking at their arrangements. This diagram illustrates a pristine deck of playing cards, fresh from the factory. It is sorted exactly by suit and number. There is only one specific arrangement that matches this perfect order. But if you shuffle the deck, there are billions of possible ways for the cards to be disorganized. Boltzmann called these hidden arrangements microstates. Because there are vastly more ways to be messy than to be organized, a system will naturally drift towards disorder. This is the statistical reality behind the second law of thermodynamics. Time moves forward simply because the universe is constantly shuffling its components from rare, ordered states into common, highly disordered ones, a measure we call entropy. But Boltzmann's peers raised a sharp objection, known as Loschmidt's paradox. They pointed out that if particles can truly reverse their paths, you could theoretically run entropy backward. So if high entropy is simply the most mathematically probable state, why did the universe begin in a state of low entropy to begin with? The forward flow of time relies on a highly improbable, organized setup established when the universe first began. To find the source of that initial order, we have to look to the stars. In the 1920s, astronomer Edwin Hubble discovered that the universe is actively expanding. If you run that expansion in reverse, tracing time back 13.8 billion years, all the matter we see today compresses into a single dense point. Cosmologists realize that for the second law of thermodynamics to hold true today, the Big Bang must have been an event of astoundingly low entropy. They call this requirement the past hypothesis. But looking back at the early universe, a chaotic, boiling soup of plasma, it hardly looks orderly. Look at this grid simulating cosmic expansion. The trick here is gravity. Because gravity is an attractive force, a smooth, uniform distribution of matter is actually an incredibly fragile, low-entropy state. If you leave it alone, gravity will aggressively curdle that smooth soup into clumps, forging stars, galaxies, and eventually the highest entropy objects in existence, black holes. By measuring the precise smoothness of the early vacuum, using a metric called the Weyl curvature, mathematical physicist Roger Penrose calculated the odds of our universe starting without black holes already everywhere. He found the probability to be 1 in 10 to the power of 10 to the 123rd power. You would run out of atoms in the visible universe before you could finish writing the zeros in that number. The Big Bang was a meticulously balanced, immaculate starting point, arrow from the everyday world up to the very beginning of the universe. But the microscopic realm tells a different story. Here, particles exist in a fuzzy superposition of multiple possibilities at once, and the mathematical waves governing them remain entirely reversible in time. That is, until they are observed. The moment a scientist measures a quantum particle, that cloud of potential vanishes. The particle snaps into a single definite location. This wave function collapse is a brutal one-way street. You cannot rebuild the initial wave from the outcome. Physicists attribute this to a process called quantum decoherence. A particle doesn't live in a vacuum. It constantly collides with surrounding gas molecules and thermal radiation. As it bumps into its environment, its delicate quantum information leaks out and inextricably tangles with the outside world. This environmental interference forces quantum potential into a fixed classical state. Decoherence serves as the engine of irreversibility, continuously pouring the concrete of history and permanently locking the barrier between the past and the future. So physics, the stars, and the quantum vacuum all obey this mandate. But how does that dictate our own internal experience? Why do our minds vividly remember yesterday, yet remain completely blind to tomorrow? The answer lies in the hardware of the brain. According to Landauer's principle in information theory, the physical act of erasing data, or recording a memory, requires the expenditure of energy. To process a thought, your neurons burn glucose and radiate heat, actively increasing the net entropy of the universe just to log the passing moment. We are burning through the low-entropy fuel of the cosmos to think, live, and build. But trillions of years from now, that fuel will run dry. The last stars will burn out, leaving behind a dark expanse filled only with dead stellar husks and black holes. This is the degenerate era. Even the black holes won't survive forever. Through an agonizingly slow quantum process known as Hawking radiation, they will gradually bleed their mass into the void. After roughly 10 to the 100th power years, the final supermassive black hole will evaporate away. What remains is the heat death. The universe becomes a vast, motionless desert of perfect thermal equilibrium. Everything is the same temperature. No energy differences exist to power a star, fuel a cell, or record a memory. Without change, time requires no direction. With total disorder achieved, every moment looks exactly like the one before it. The arrow of time finally dissolves, returning reality to the timeless, symmetric void from which it began. It is easy to view the arrow of time as a tragedy of decay, but that relentless march toward disorder is the exact mechanism that actually breathes life into the entire universe. We exist only because the cosmos started in a state of impossible perfection, giving us the energetic runway to evolve, adapt, and build complex biological structures. Albert Einstein once remarked, "The distinction between the past, present, and future is only a stubbornly persistent illusion. We are just localized pockets of order, briefly riding the thermodynamic current. We cannot pause the clock, and we cannot reverse the flow. But out of all the chaotic matter, we are the only known pieces of the universe capable of looking back at our own history." We get to witness the beauty of the asymmetric dance long before the music stops.